So in this particular lesson, 4.3, Integration Properties, we'll be looking at the characteristics of definite integrals that we can use to evaluate exact areas between the curve of a function, the x-axis, instead of just approximations. So this is our first step from approximations to an exact answer. So the first thing we're going to do is define the definite integral as a limit. So recall here that the idea behind a definite integral in terms of an approximation is that we break the area between the curve and the x-axis, okay, into multiple rectangles that we can use to approximate the total overall area. All right, the idea being is that we take the area of each individual rectangle, okay, starting at some x value, x equals a, and we add together all of those areas of each individual rectangle, with each individual rectangle having an area of height, or the function value of that specific x value, times the width, our delta x, the size of our subinterval. So we get that our our definite integral is approximately going to be equal to the sum of the area of each individual rectangle of height f of a plus k delta x, where k dictates at what rectangle we're at, and delta x dictates the width of each rectangle. So if we want to get a more exact and accurate answer for the area between our curve and the x-axis, what we need to take note of is that if we add more rectangles, all right, to a specific curve, we're going to get a more and more exact answer. We can see as we move from blue to red to green to yellow, as we add more rectangles, we can see that this area between the curve and the x-axis becomes more and more representative of the actual area between the curve and the x-axis. So if we want to go ahead and get an exact answer for the area between the curve and the x-axis, what we can do is keep adding these rectangles underneath the curve and the x-axis, which if we imagine that if we keep adding more and more rectangles, we'll get an exact area. These rectangles will fit exactly to the curve. So the idea here is we're going to let the number of our rectangles go to infinity. The idea being, again, that the more rectangles we add, the more accurate area we'll have. So if we keep adding rectangles in practice, that's going to lead us to get an exact answer for the area between the curve and the x-axis. So as a result, we write the definite integral is equal to the limit as n goes to positive infinity of our Riemann sum. All right, so here again we have our definition that the definite integral is equal to limit as n approaches positive infinity of our Riemann sum right here, okay? Just as the same way with the derivative, they won't expect you to make actual calculations with this limit, but they will expect you to recognize what this limit entails and what this limit represents mathematically, okay? So let's take a look at an example here of writing a definite integral as a Riemann sum, okay? So let's write the definite integral of the natural logarithm function from x equals 0 to x equals 6 as the limit of a Riemann sum. Citing the prior equation, we know that f of x is going to be equal to natural logarithm of x. We compare the two equations and we see that that holds, okay? We see that a is equal to 0 and we see that b is equal to 6. So as a result, delta x is going to be equal to b minus a divided by n, or 6 minus 0 divided by n, which is going to give us 6 over n. Thus, the definite integral can be written as the limit as n goes to positive infinity of the summation starting k equals 1 until n of the natural logarithm of a plus k delta x times delta x. Again, all I've done is I've cited the second part of my equation right here, where I have f of a plus k delta x, where f in this case is natural logarithm of x, so we're going to have natural logarithm of a plus k delta x. All right, so now what we do is we make the substitution for a and for delta x. We know a is equal to 0, so this is going to reduce down to just k delta x right here, and we know delta x is equal to 6 over n, so we're going to have k times 6 over n, which is what we end up with our expression right here at the end. And then our delta x we're going to replace with 6 over n, which gives us our completed equation. So properties of the definite integral. All right, so definite integral has some properties that are very similar to derivatives. All right, so constant multiple. When integral is multiplied by constant, the resulting area is scaled by a factor k, okay? The same way with derivatives that we can factor out a constant multiple from the derivative, we can factor out a constant from a definite integral such that our answer in the end, when all is said and done, is going to be equal to that constant times the definite integral of that function. Again, the idea is that we're scaling this area by a factor k. Sum and difference of integrals, okay? If we have two functions f and g added or subtracted, and we're interested in definite integral of those two functions from a to b, this definite integral will be equal to the individual definite integrals of each individual function added or subtracted from each other. Lastly, we have the property known as area splicing. Well, better said, not lastly, there is a couple more properties that need to be covered next slide. So area splicing. Since the integral is represented the area between a graph and the x-axis over an interval a to c, the integral is the sum of all areas between a and c. All right, so you can see right here from a to c, this integral from a to c of f can also be rewritten as the sum of all of the areas that make up the interval between a to c. Say, for example, the area from a to b and b to c. So as a result, what we can do is we can write the integral from a to c of this function f as equal to the integral from a to b plus the integral from b to c of f. Again, the idea being is that the overall area represented by this definite integral from a to c is equal to the area from a to b and the area from b to c. Other properties of definite integral, equal bounds. All right, so if we have equal bounds, say from a to a, if the lower bound is the same as the upper bound, then our delta x is going to be equal to 0. There's no change in x occurring, and thus the area of the region will be 0. And lastly, we also have what's known as bound reversal. If the lower bound a and upper bound b are switched, then delta x will become negative. Okay? So if we have from b to a now instead of from a to b, delta x will become negative, so that's going to be equal to negative definite integral from a to b. So all that happens when you reverse the bounds is there becomes a negative sign that becomes attached to your resulting definite integral. So let's look at an example of evaluating properties of definite integrals using geometry. Okay, so provide the graph of a function g of x below. Determine the integral from 20 to 0 of 2 times g of x dx. Excuse me. So here's our graph of g right here. So first thing we can take note of is that our lower bound in this case is 20 and our upper bound is 0. So we can actually do a bound reversal here, all right, where we can rewrite this as the definite integral from 0 to 20 with a negative sign attached, okay? In this case, it's always easier to go from the lesser value to the higher value because that means we can proceed to work from left to right instead of the more confusing case, right to left. As with the right to left case, if we were to work from 20 to 0, we'd have to remember to take that negative sign into account, whereas if we write that negative sign right at the start, we don't have to remember it because it's already accounted for. All right? So next thing that we're going to do is we notice we have a constant multiple of 2, so we can factor out this constant multiple of 2, and that gives us negative 2 from 0 to negative 2 times the definite integral from 0 to 20 g of x d of x. And then the last property we can use now is we can recognize that we're going to have different areas over different intervals, so we can perform area splicing over the respective intervals of interest. So we see that we have a triangle from 0 to 10, another triangle from 10 to 15, and lastly, one last triangle from 15 to 20. So we can break up this integral from 0 to 20 into 3 different intervals from 0 to 10, g of x d of x, plus 10 to 15, g of x d of x, plus 15 to 20, g of x d of x. So now we can proceed to evaluate the areas of each respective integral, okay, which is going to give us, for the first integral from 0 to 10, 1/2 10 times 10. For the second area, minus 1/2 5 times 5, again minus because this area is negative right here, plus 1/2 5 times 10 for the final integral from 15 to 20. So as a result, that's going to give us, when we evaluate all this, minus 100 minus, on the outside, 100 minus 25 plus 50, which when you evaluate will give you minus 125. And these are the basic properties used to evaluate definite integrals.